So another parabola here. How do I know it's a parabola and not something else? That's a good question. And perhaps I should have started out with something more like that. But when you're looking at this, it's a parabola. But how do you know? How do you know it's a parabola? Well, maybe I should kind of run through this real quick. This is on the back of your handout, the last page here. Conic sections a lot of times are written in this form like this. And then you kind of play around with these things to try and figure out, well, which conic section it is. The first and easiest cut to decide whether or not something's a parabola is if one of these is 0. That is, either A or C is 0. Essentially, that means you have one squared term. So I kind of, is A or C 0? That really translates to there's only one squared term. If there's only one squared term, then you're dealing with a parabola. Simple. And in our current case, we're dealing with exactly one squared term. So it's a parabola. Now, if you answer no, then you got to go down an even deeper rabbit hole. So are A and C opposite in sign? Now, those are the coefficients of your squared terms. If you have one of them is positive, one of them is negative, then you're dealing with a hyperbola. So the answer here is yes, you're dealing with a hyperbola. If it's no, well, then you got one last question to ask yourself. Are A and C equal? If A and C are the same value, then you're dealing with a circle. So you got a circle there. How about over here? Well, if A and C aren't equal and you've branched all the way down here, then you're stuck with an ellipse. So that's how you can work your way down some of these. Let's see if we can't practice with that, and maybe I'll do 2 of these with you. So for instance, let's take a look at the first one. Is there just one squared term? No. So I branch down to here. Are A and C opposite? It is the coefficients of the squared terms. Are they opposite in sign? Yes. So if they're opposite in sign, you get an early exit ramp from this little list here, this little tree diagram. And yeah, that's going to be a hyperbola. Nice. How about down here? Well, with example D, there's a little something that you got to be aware of. And that little something is up here. You have to have this thing set to 0. So before you work with example D at all, you've got to rewrite it. All these terms on the right-hand side have to be moved to the left-hand side. So it'd be 25x squared minus 100x plus 25y squared plus 200y plus 275 equals 0. Okay, let's hit our little tree diagram up again. Are A and C both 0, or is one of them 0? No, you've got 2 squared terms. Okay. Are they opposite in sign? Are my squared terms opposite in sign? No, they're both positive. Are they equal? Yes. So now you've got a circle. If you were to graph this, I could type this equation in right now into Desmos and it would graph out a circle. So, nice. So it's nice to understand what you're looking at before you start graphing these things. Because then you know that, oh, I expect 1 focus or 2 focus. Should I expect a hyperbola, parabola, what I should expect. Let's go back to here. And let's start with kind of a basic question. Where's the vertex of this going to be? It's no longer like our first one at 0, 0. It's been shifted. So what my suggestion to you would be is to look at that equation and figure out, well, where what value is going to make these terms equal to 0? So this is example B. X plus 1 squared equals 4 times y minus 3. Oops, not squared. That would be a different kind of conic section, probably a degenerate one. Let's write ourselves a little t-table and keep track of some of this information. Where's my ruler? Now, as far as the vertex is concerned, we can kind of read that off. Ask yourself, what makes this squared term equal to 0? What value of x? -1. And if that's -1, you get a 0 on the left-hand side, then you have to have a 0 on the right-hand side. That's only going to happen when y equals 3. So there's your vertex. Which way is this going to open? Up, down, left, or right? Yeah, opens up, because you have a positive squared term. If you had a negative squared term, then it would open down. Now, as far as figuring out, P and then your focus and directrix and all that good stuff, I've got to get the y term by itself. I don't want a coefficient out here. I need to put that number over to here. So I'll multiply both sides by 1/4 and get this. And now this becomes my A term. So that number is A. A is 1/4. Remember, we can solve for P. P is 1 over 4 times A. So 1 over 4 times 1/4 gives me 1 over 1, or just 1. All right. Let's graph a couple things. So one of the things I want to graph would be the vertex, which is at -1 and 3. -1 and 3. So that's going to be up here. And to find the, let's see, this is going to open up. And we can actually calculate the y-intercept. How would you find the y-intercept? Set x equal to 0. So you can find the y-intercept. I'm not really overly interested in that right now. But if I wanted to find the focus, I got to go up by 1. So that's going to be right here. What are the coordinates of that focus going to be? Yeah, -1 and 4 would be the focus. Down 1 is going to be the directrix. And that's going to have an equation. The equation of that directrix should be y equals 2. And then you're going to have a graph that opens up. Let's see, 1/4 plus 3. I think it'd be 3 1/4 is where this graph should cross the y-axis, if I did that right. It's going to be kind of a wide opening parabola. Not a really good job there. My apologies. But I think we've got all we need here. We've got the focus, we've got the directrix, and the y-intercept, I'm pretty sure is going to be 3 1/4. 0 and 3 1/4. Let's write that as 13/4, like that. Yay, and that's it. Okay, let's keep.
Back to your T-table.
Sure.
Thank you.
Yep. Now, one of the problems that you're going to run into with working with some of these things is that on your graphing calculator, you're kind of limited on what you can do in terms of being able to graph things because you have to have y solved for. So for in this case, I'd have to rewrite this as y equals 1/4 x plus 1 squared, and then it'd be a plus 3. That's how you could graph this. That becomes harder if you have something like you do in example C here. So in example C, I'm not going to spend the time on this here. You can kind of check it out later if you want. What you'd have to do is you'd have to solve for y. That means taking the square root of this, and yes, this is defined. X just has to be negative there. But remember, there's a plus and minus to that square root. So to get the negative square root, you can do this. And I think I've got some of the keystrokes for that in here, so you can put those in. And then you can graph it. So you can play around with that if you'd like. We're going to move on down to example D here. And working with the equation below. So we got 4 equals 4x, or x squared plus 4y squared. And I'm hoping that some of this stuff is sitting back there in the back of your mind, and it just needs a little dusting off. What kind of a conic section is this going to be when we graph it? An ellipse. Good. It's going to be an ellipse. It helps us if we get a 1 on the left-hand side. So I'm going to divide everything through here by 4. 4 over 4 gives me a 1. I'll have an x squared over 4. 4y squared over 4 is going to simplify. In fact, I'm going to simplify this a little bit more. I'm going to write it as x squared over 2 squared plus y squared over 1. But there's an interesting thing about 1. 1 and 1 squared are the same thing. So write it as 1 squared out of convenience. Let's graph this thing now. Because the squared terms don't have anything else with them, it's just x squared and y squared, the center is going to be at 0, 0. That's what makes the squared terms equal to 0. To find the vertices, I want to go to the left by 2 and to the right by 2 and then up by 1 and down by 1. That corresponds to the square root of these denominators. So square root of 2 squared is 2. So I'm going to have a vertex here and here. Square root of 1 squared is 1. And I get something kind of like a cigar shape. The only thing I ask when you graph these things is that you give me something nice and smooth. If you play connect the dots and give me a diamond shape, I'll be kind of unhappy. So try and make it look, somewhat smooth and round. It actually has derivatives at some of these points. To find the focus, we've got 2 different axes here. One of them's longer than the other one. So this longer one is the major axis. Any guesses what that shorter one's called? The minor axis. So to find that, the focus, you have to calculate something called c squared. C squared is going to equal the larger of these squared minus the smaller one squared. In our case, 2 squared minus 1 squared. So c squared equals 3. So c is going to be the square root of 3. You're going to move that distance away from the center along the major axis. So square root of 3 is about 1.732, and negative square root of 3, likewise. If you're asked for these on a test, I expect these kind of points. Don't give me decimal values, please. Just give me nice exact values. Okay, let's let's do one last example here. I think we're only going to have time for that one more. It's going to be example F. How do I know that this is a hyperbola? I got two squared terms. Go ahead, Clyde.
Square terms have opposite signs.
Yeah, the squared terms have opposite signs. So let's take this. 4x squared minus 16y squared equals 64. Now we saw in the last one with our ellipse that I was convenient to divide everything through and get a 1 on the right hand side. So this time I'm going to divide by 16 or 64 on both sides and see if I can't simplify that. That's going to simplify down to x squared over 16. X squared over 16. Can I do a little bit more there? Yeah, 4 squared. And then y squared over 4, but that's really going to be y squared over 2 squared equals 1. Because both squared terms have a don't have any like x minus something or x plus something, what makes the squared terms equal to 0 is x equals 0 and y equals 0. So 0, 0 is the center of this. Now what you're going to do to graph this one is we're going to draw a little box. And this has kind of been drawn for you a little bit. Let's see how we find that box. The vertices of these box is going to be found by finding the same points that you would graph if you were graphing an ellipse. So I'm going to move 4 points to the right, and I'll have a point at 4, 0. 4 points to the left, so I have a point at -4 and 0. I got to do likewise up and likewise down. Up 2, 0, 2. Down 2, 0, -2. And now you're going to do something that might seem kind of strange, and that is you're going to play connect the dots in this fashion. We're going to draw a rectangle through these points. Now this rectangle is just for your convenience in graphing the hyperbola. After you draw the rectangle, you're going to do some more work. I kind of regard this as like scaffolding. If you see somebody working on a tall building, there are some scaffolding so they can stand up there and do their work. We're building the scaffolding for ourselves right here. So I need the diagonals of this rectangle to kind of guide where my hyperbola is going to be. Now I apologize that this is going pretty fast. Hopefully it is review that I think it is. Because the x squared term is positive, this is going to open left and right. So we're going to start here at the vertex and draw a parabolic kind of shape that approaches but doesn't quite touch the asymptote here. Likewise down at the bottom. And then again here and up here. Now if you actually accidentally touch it or cross it, that's fine, but you know, try and make it approach but not touch these things. There's your graph. That's a lot of what I'm looking for. There's one last thing we've got to find here, and that is these points here and here. So if you look on your graph, you're like, oh yeah, he did sneak something else in on there for us. Those are the foci. Just like ellipses and parabolas, you have foci for hyperbolas. They're inside each branch of the hyperbola. Now, whereas when we're dealing with x squared over a squared minus y squared over b squared. And actually, if I had a plus here, I used to calculate c squared equals b squared minus a squared, or a squared minus b squared, to find c. That was for an ellipse. But if we're dealing with a hyperbola, then that formula changes. When you have, say, x squared over y squared, no, x squared over a squared minus y squared over b squared, your calculation for c is going to be different. C squared is going to equal a squared plus b squared. And that's the formula we're going to have to use here. Now the difference is, if you use the wrong formula, you're going to get foci that are going to land inside the box. That's what's telling you used the wrong formula. If you use the right formula, then you should get foci that are far enough away from your vertex that they're going to lie inside each branch of the hyperbola. So let's finish this off with a calculation of c squared. So c squared is going to equal 4 squared plus 2 squared. So that means c squared equals 20. So c is going to be the square root of 20. The square root of 20 is going to be 4 something, about 4.47, probably about 4.5. Keep in mind your vertex here is a distance of 4, so this is just far enough to get inside here. If I use the wrong formula, if I did 4 squared minus 2 squared, I'd have a total of 12. Square root of 12 would put me in here. The foci then are going to be at the point square root of 20 and 0, and negative square root of 20 and 0. So, whew, that does it. There's probably a bunch of other problems that I'd like to solve on this one, but we're out of time. So, any thoughts or questions? All right. Yeah, everyone's done. It's like, no, I'm done. Can I be excused? My brain is full.